remember, our whole goal here was to model this time as the time of impact if I were not to bend my knees. So let's come back to the equation we had, which was the net force equals change in momentum over change in time, and walk through each individual piece of this. Jacob, the question is, what changes when I don't bend my knees? So if you look at the equation here, does the mass of my body change if I don't bend my knees?
No.
No, so the mass is the same. What about the final velocity after colliding with the ground? If I don't bend my knees, does that change? It's no longer 0. I'm still going to stop. So that's the same. Mass, what about the velocity initial? What about the velocity right before I strike the ground if I don't bend my knees? Does that change the,
No.
It doesn't. So notice, the entire top of the equation is the same. It's only the time that changes if I don't bend my knees. So we have the net force is equal to 0 minus 68 multiplied by negative 4.2233 divided by the time during the collision, 0.0005 seconds. And that, again, is in newtons, and we want to convert that over to pounds so we have an idea of how much force that actually is. 4.448 newtons on the bottom, pounds on the top.
129,129.
That's fine, that's plenty. So with sig figs, approximately 130,000 pounds of force goes through my body if I don't bend my knees.
That's a lot.
So let's back up. If I bend my knees, it's 220 pounds. If I don't bend my knees, it's 130,000 pounds of force that goes through my body. Will this actually happen? Will I get 130,000 pounds of force going through my body? Will it happen, class?
Yes.
No, there's no way. Why not? Travis?
Because you're never going to not bend your knees.
No, that's not true. If I didn't bend my knees, yes, Travis. Andy?
Because you're not a golf ball and you won't, like...
No, it's not about whether I'm a golf ball. The time of impact is kind of just, it's a good example here. Hamza.
Is it because you don't break?
I will break! There's no way that I can withstand 130,000 pounds of force. So something will break. So this won't work. Yes, from a theoretical standpoint, this is the force that would go through my body. But no, because something will break, and therefore, because when the force gets high enough, something's going to break in my body, and therefore I wouldn't actually withstand this much force because it just didn't happen because something broke. Okay, there are all sorts of examples in your lives that deal with this, where the time of impact is changed to change the amount of force acting on your body. Yes, you should bend your knees. The more you bend your knees, the less force acts on your body. Give me more examples where we change the time to change the force of impact during a collision. Austin.
Crumple zones in cars.
Crumple zones in cars. We're going to talk about that one. The whole front of your vehicle is designed as a crumple zone to decrease or increase the amount of time during the collision, therefore decrease the amount of force during the collision. And
One of those playscape blob things in the water, it's like the decrease in acceleration is also like...
sorry, did he say playscape blob things?
You know the thing that some person jumps off of and launches another person? That's the
The
collision.
playscape blob things.
You know those things that you jump off a huge platform and land on a huge airbag and launch someone else?
Fair enough. It's a huge airbag.
Yes.
We'll go with that. It's a huge airbag, and basically what it does is because it has a large distance, it decreases or increases the amount of time, therefore decreases the force, so you don't get hurt when you land on the large playscape blob.
Launch someone else.
Yes, and you launch someone else, they get a force as well. Travis.
Airbags.
Airbag. So again, going with the airbag concept, we'll talk about the whole vehicle a little bit more. We'll talk about safety belts, airbags. What else though? Not looking at cars. There are all sorts of examples. Jay.
Your soft bed.
Your soft bed. You can jump on your bed and it doesn't hurt. If you were instead to jump on the floor, for example, that would probably hurt. True, just a very basic example, difference between the two. Because the time of impact with the floor is going to be a lot less, therefore it will hurt more. Travis?
Moon bounces.
Say again?
Moon bounces or bounce
Moon
bounce.
bounce. We're sticking with the whole bounce concept here. Sure, that's the exact same thing. But you also have the same thing with your shoes, right? We could talk about the same thing with the packaging that you use when you send something through the mail. When you put something in a box, you tend to put stuff around it that is soft so that, and the mail carrier throws it in the back of the vehicle, it will land, and therefore the time of impact will actually be decreased or increased, therefore the force will be increased. We have other items, like this one, for example. Can I please, let's do, this will work. If I take this item, a toy, I take it and I put it right here, it's going to go up to approximately that height. I'll do it again, so you can see it'll go all the way up to that height. If instead I take it and I put it on the notebook, it only goes up to there. Notice the difference. On the notebook, it goes up to here. On the desk, it goes up to here. Why? In.
The notebook absorbs some of the, like, when it hits it takes longer for it to,
The collision actually takes longer with the notebook, which decreases the force on the toy, which decreases the acceleration of the toy, which decreases the height it can go to. But when it's on the desk, it can go to a much higher height because the time of impact is much decreased. Coming back to the concept of the vehicle, I have for you a video provided to me by, and we're going to have product placement here, Ford Motor Company, because they gave it to me. I felt like I should leave this on here. Ford Motor Company, this is a video of a car crash. This is with your crash test dummies in it, showing the whole event for a car crash. The first one obviously is in real time. Every one after this is going to be in slow motion. The first thing you should notice is the dot. Every time you see that dot is the very beginning of the collision with the wall. Because they're going to show a whole bunch of different angles. That dot helps you to always see when the collision occurs at the very beginning. We talked about crumple zones. The entire front of the vehicle, this portion right here, if you watch it during the collision, is going to crumple. The whole reason that that crumples, I mean the whole thing, the engine, the hood, all the stuff, the bumper, everything in front of the car is designed to crumple. So that what happens is it increases the time for the collision and therefore decreases the force during the collision. The whole goal here is to decrease the forces acting on the car and therefore on you during the collision. So here you can again see the crumple zone. Then of course we could talk about the airbags. During a collision, your head has a choice. It can run into the steering wheel or the dash, depending on which side you're on, or it could run into the airbag. When you run into the dash or you run into the steering wheel, the time for that collision is actually going to be very small. But if instead you run into the airbag, you have a lot longer distance for your head to stop, and therefore the time for that collision is much increased, and the force for the collision is decreased. One thing you should notice right here, they actually paint the dummies' faces so they can see exactly where on the airbag the dummy's head ran into it, so they can analyze and learn how the airbag is working. So again, oh, and your seat belts. Your seat belts are actually designed, most people don't realize this, with something called a torsion spring in them. The torsion spring is basically a cylindrical piece of metal that you twist. So when you get in an accident, it actually takes and twists that torsion spring and twists it permanently in such a way that you actually have to have the whole seatbelt assembly replaced if you get in an accident, because that torsion spring actually absorbs a lot of the energy. It increases the time for the collision and therefore decreases the force during the collision.
Is that the reason why your seatbelt gets locked every once in a while?
Your seatbelt gets locked, actually, that is just a design on the idea that the faster you move it, you might be in a collision. So that the faster it moves, it actually locks. It thinks you might be in a collision when you do that if you try to do it too quickly.
That's annoying.
Well, it's not annoying if you get in an accident.
Yeah, that's
So, if you take anything away from today's lecture, the one thing you should remember is this: wear your seat belts. Jay, why should you wear your seat belt?
So So that the time of the collision increases.
The time of the collision is increased, therefore
There's less force.
there's less force on your body, and therefore you stand a much better chance of coming out of the accident with fewer injuries. In addition to that, just going to throw it out there, you could drive more slowly. This will decrease the force as well. It'll also save you money in the form of hay.
Use less horses.
Uses less horses, thank you. Fewer horses can you, but in this case, I guess it would be less horses because you could have half a horse. Because we're talking about horsepower.